All right. Okay, thank you. All right, so Mike Kolian has been an EPA scientist for 20 years and has a comprehensive history of past and current climate science, including research, observational data sources, communication, and contributions to the peer-reviewed literature. Mike manages EPA's climate program and works with partners, researchers, and data contributors to develop and publish climate-related indicators. Mike also works with the U.S. Global Change Research Group as co-chair of a federal interagency work group focused on advancing the science of indicators and was an author on the most recent Fourth National Climate Assessment. And so with that, I want to welcome you, Michael, and I'll let you take it away.
Great. Thank you very much. I'm delighted to be here and just kind of soaking in the first few sessions here and talks has just been really delightful. And so I'd like to just make sure I do my job and tell everybody I'm here to sort of moderate the session. We have an outstanding selection of panelists on this session one, which is addressing warming temperatures and changes that are affecting California directly, some of the weather and larger scale things that are in play, and also having an effect in delivering climate and weather patterns to California. So this session offers a great deal of connections, and hopefully we're able to highlight those. For me, just to introduce people a little bit into where I am at, I'm in Washington, D.C. I've been with EPA for several years now in the Office of Atmospheric Programs. I started out working on many of the programs that support the Clean Air Act. So we have a cap and trade program starting through the Clean Air Act amendments of 1990. And we brought in the emissions data from power plants, but we also had programs to assess the effectiveness of those programs. And so I managed ambient air quality networks and other monitoring observational systems that allowed us to develop indicators to assess whether the effectiveness of those regulations were working, improving conditions. So my roots is in monitoring and observations. Subsequent to that, I moved to the Climate Change Division within the same office of EPA. I've been there over the last decade, working on climate change indicators. We have a very similar philosophy to California's report and effort. And I've known Carmen for quite some time now. We have sort of a national scale indicator set that EPA manages in very similar ways, in which we're tapping into data contributors, good science that's out there, leveraging that, bringing it together to bring this weight of evidence together across the country. As Arit alluded to, I'm also co-chair of the U.S. Global Change Research Program's Interagency Climate Indicator Working Group. And so there it is a more federal-centric, yet tapping into many data sources, effort to highlight climate indicators that may feed into and inform the national climate assessments that USGCRP puts into place. So many connections relative to me into this effort. So one of the reasons that I hope to bring some connections and facilitate this session. So let me quickly turn to our panelists and start introducing the esteemed group that we have pulled together. Incidentally, each panelist will present for roughly 15 minutes, and then, as Arit alluded to, we'll have a discussion for roughly a half hour after that. So we really encourage participation, your questions along the way. First, we have just to roll through each, and then we'll have Mike Anderson kick off. But first, to kind of roll through the panelists, we have Dr. Michael Anderson from the California Department of Water Resources. He is the state climatologist for California, and it's a combined position between the state of California and NOAA, and he provides climate data services. I'm sure is quite busy doing just that. He works in the area of extreme events, subseasonal to seasonal forecasting, adapting to climate change. He's very active in the research community and supports efforts through the Department of Water Resources. He is a graduate, has done some graduate and postgraduate work from UC Davis in the area of hydroclimatic system modeling and monitoring and evaluation. So we're very happy to have Dr. Anderson with us. So welcome, Michael. Next, we have Dr. Ben Hatchett, and he is with the Western Regional Climate Center, which is also based on the Desert Research Institute. He is a Northern California native, a regional climatologist at the WRCC. He has studied geography, hydrogeology, atmospheric science from the University of Nevada. His professional experience spans many fields, including the laboratory and computing environments, and has a central goal of a research aim to develop actionable science that promotes positive change. Welcome, Dr. Hatchett. So next we have Dr. Marty Ralph, and he is with the Scripps Institute of Oceanography at UC San Diego. Dr. Ralph is a weather and water scientist focused on understanding the origins of floods and droughts and improving predictions for water management and flood control. Leading expert on atmospheric rivers. So I suspect we'll be hearing quite a bit about that, and is a very important topic for California. Has been with NOAA for over 20 years, many peer-reviewed articles, and has a BS in meteorology and from the University of Arizona, Ph.D. from UCLA. And then, so welcome, Mr. Ralph, or Dr. Ralph. And then we also have Dr. Samantha Stevenson from UC Santa Barbara. She is a climate modeler interested in how climate change, both past and future, affects natural variability in climate. These have, important implications for extreme events, drought, flooding, and wildfire. She is an assistant professor at UC Santa Barbara, and she's been a research scientist at NCAR, graduate work at University of Colorado, Boulder, followed by NSF Ocean Science postdoctoral fellowship at the University of Hawaii and Manoa. So there's a lot that we'll be hearing about from this group, and we're excited to learn more about these larger scale processes and how they affect each one of these folks works in their scientific inquiries and endeavors, but also turning that around and how that might inform decisions about resiliency, adaptation, decisions on the ground. So this is a really great crossover group. And without further ado, I will introduce the first speaker, and that is going to be Dr. Anderson. So please take it away, Dr. Anderson.
Mike, your audio is not working for some reason.
So I think as we tune up Mike's presentation, I guess we're having some audio difficulty on Dr. Anderson's end, but we'll...
Cannot hear you yet, Mike. We'll give Mike just a quick minute to try and get back on, and then if not, we can go to our next speaker and come back to him.
Okay, and yeah, maybe if Mike, if you could chat in what might be happening.
Yeah, maybe he has to reconnect. So why don't we move forward to our next speaker, and we can come back to Mike. Our next speaker is Benjamin Hatchett.
All right. Hello, everyone. Cool. You can all see my screen.
We can see you and hear you, yes.
All right. Cool. Well, thank you very much for the opportunity to share some thoughts and insights and perspectives and a lot of photos with you all today. I'm really excited to join in the conversation. And what I would like to highlight are kind of the range of time and space scales that our weather and climate extremes occur over in California, and try to highlight or try to draw out some of the connections between them, their consequences, and then also discuss some of the lessons that I've been learning through some of the recent collaborations. So we'll talk about a lot of different things, see a lot of pictures, and hopefully that will kind of weave a thread between many of the other wonderful presentations that are on the menu for the coming days. So I'll start off with the issue of time and thinking about the time scales at which many of our weather and climate extremes take place over. So at the faster time scales, we typically are thinking less than hours, so even upwards of in the minutes to seconds time scales. And when we think about these time scales in terms of precipitation, we're really thinking about the high intensity, short duration precipitation events that can trigger mass movements such as avalanches on Mount San Gorgonio, shallow landslides into the Tuolumne River that ultimately kick 16 times the annual sediment flux down the river and cause some challenges for the water resources infrastructure downstream, Montecito debris flows, heavy snowfalls causing traffic jams over our favorite roads to access skiing. And also when high intensity precipitation occurs over our urban areas, not only does that pose the urban flooding challenge, but it also ultimately reduces water quality. This is a view of Newport Beach, not looking so lovely for a swim after a big storm event in February of 2019. We also want to think about windstorms. And even though windstorms can last from hours to days, as I'll show on the next slide as well, it only takes a few minutes or seconds of a strong gust of wind to ignite wildfires or knock over a semi on the road, causing transportation impacts. And at any given hour, we can have a large area of the state undergoing downslope winds. This image in the middle here is showing 10 a.m. all of the different grid cells over California that were experiencing downslope winds during the 2018 Camp Fire that burned paradise, and also was causing some headaches in the North Bay and North Coast regions. And then another very, very fast timescale process is actual lightning, which we got a unfortunate reminder of last year, or sorry, not last year, last August, with our lightning siege that triggered a number of fires throughout the state, primarily in the northern half of the state. But even though the moisture transport to produce the lightning occurs at a much slower time scale, the individual lightning events themselves were happening just over the time scales, split seconds, but really over a matter of minutes to hours, and a number of fires were kicked off by that event. So moving more into the hours to days time scale, this is where we still want to be thinking about winds and longer term, longer duration, I should say, wind events, which increase the probabilities of ignitions, increases wildfire spread, the timing and number of days with which these wind events take place is very important. For much of California, we see a lot of numbers of days with downslope wind events in the winter season, which is primarily important for Southern California, Santa Ana wind events, but as well in the fall season, the end of our increasingly extended dry season, which we saw time and time again over the last few years, and particularly this year with large wildfire growth taking place at the end of the dry season with some of these colder offshore wind events. We also want to be thinking about heat on the timescales of hours and days, because that has strong implications for public health, energy demand, and also drying of fine fuels. And just an example here from California's hottest region, Imperial Valley, we're starting to see trends towards an increased number of extreme heat hours using the National Weather Service thresholds for heat index. We're seeing peak summer becoming even hotter at the hourly timescale, as well as the maximum and minimum daily temperatures. So we're starting to see not just days warming, but individual hours accumulating warming as well, which increases exposure to heat. We also want to think about, when we're thinking about fire and wind and heat, smoke transport and air quality, because those are compounding factors. If it's extremely hot and you're stuck inside and the power's out and the air quality is bad, that's not a really good situation. And we saw a lot of days this year with all of those factors coming into play, with transport of very poor air quality from the numerous fires burning across the western US. Thinking in terms of precipitation, we start thinking about atmospheric rivers, as Dr. Ralph will talk about, which really drive our multi-day precipitation extremes. And when we start discussing those, we're thinking more along the lines of riverine flooding, rain on snow type flooding, water resources, and some of these slightly longer duration processes. Moving into the longer seasons to years time scales, this is really where we start seeing trends emerging at these longer time scales when they're occurring year after year after year, such as summer times are becoming increasingly dry. The vapor pressure deficit is an indicator of atmospheric thirst and correlates very strongly with wildfire acres burned, and likely with burn severity as a result of drying out of heavier fuels and allowing for more intense fires to burn over larger areas. Coincident with that is the increase in heat, leading to longer period energy demands. When we start thinking about precipitation in these longer timescales, now we're really thinking about things like drought, which is driven largely by the number of atmospheric rivers that make landfall, and drought operating both at monthly to seasonal timescales and also multi-year timescales. Also, we want to be considering of the phase of precipitation. So whether that precipitation is falling as rain or snow is extremely important for whether or not our snowpack will accumulate and ultimately melt into our reservoirs. But as we see in the upper right-hand side, we're seeing decreases in the percentage of precipitation falling as snow, meaning that that precipitation now is being managed as a hazard rather than a resource. So dealing with it as a flood issue rather than something that accumulates in the mountains for later melting and inflow into reservoirs to provide for water resources. At the even longer time scale, the last decade has been pretty insightful in terms of providing us with this millennial perspective of just how extreme have some of the years that we've seen been in terms of our paleoclimate perspective. And so a couple examples just from the 2012 to 2017 period, the 2012 to 2016 drought, we found that that's on par with some of the more severe droughts of the last 10,000 years. So the medieval mega droughts of the medieval times, when Beowulf was being written in about around 900 AD. Our recent drought, hopefully not our continuous drought, is similar in terms of precipitation reductions to that year. However, the big concern is it's warmer now than it was then, or in some of our other historic dry periods. And within that year, within those years, we also had 2015, which had record low snowpacks that were estimated to be some of the lowest, if not the lowest, snowpacks on record using dendrochronology dating back to upwards of 500 years. So extremely dry and low snow situations. A couple years later, we got a glimpse into what an average year in the wettest time period in the last 20,000 or so years. So since the last ice age, 2017 gave us precipitation that was roughly on par with what we would expect to see during the deglacial period around 16 to 18,000 years ago, when large lakes filled the Great Basin. Many of those lakes filled up in 2017 to give us kind of an idea of just how wet things can get. And so within the span of really just 3 years, we saw almost how dry things can be and just about how wet they can be. So now we talked about time, let's think about space. And here we're really just going to want to think about the different space scales that these impacts occur at, operate upon, and can scale up towards. And so we can really think about all of these different impacts in terms of heat extremes at the very most local level, but scaling up to regional levels where we're considering larger areas of sensitive populations and energy demand, impacts of wildfire on our natural resources, such as our parks being closed after all the trees burn and then fall on the trails, water resources, such as reservoir levels dropping with time, and how that sort of scales from a local reservoir being at low levels. But when that reservoir provides much of the state with water resources, that's really a extension of those impacts from north to south. Sensitive populations, such as our essential agricultural workers being exposed to heat, making sure that they are protected in these extreme heat events, and then fire danger, both at the neighborhood levels all the way up to the forest levels. And when we scale this up to the state level, I think that's where a lot of these challenges really start to emerge. August was a prime example of the straining of firefighting resources when hundreds of fires were burning throughout the state, with numerous very large fires, or arguably mega fires in one example of far northern California's August complex, straining resources and causing challenges for local populations. Those impacts then become scaled to regional levels when we start thinking about air quality reductions throughout much of the western US. Perception of heat is an important aspect to consider, in that our hottest regions, Kern County, the Central Valley, Imperial County, have a very high heat perception risk, which is good, but there's less heat perception along the highly populated and often vulnerable coastline regions. And that's a little bit concerning as we start to see trends towards increasing heat events, particularly in these coastal areas. During the winter season, similar issues can arise in terms of statewide water management and emergency response, the conveyance of water to minimize flooding, or the allocation of resources to handle mass movements. The February 2019 event was a great example where we saw many rivers throughout the state above the flood stage. And one last global perspective from the fires. This is looking using a NASA satellite showing the aerosol index, so how much smoke particulates are in the atmosphere. Fires along the western coast of the US, which is kind of in the left-hand side there of the image, that smoke gets transported and causes reductions in visibility and air quality at the continental and at the global scale. And ultimately, in certain cases, this smoke was transported into the Arctic, where it then can be, these darker particles are deposited on sea ice and snow, reducing its albedo and leading to additional warming of the Arctic through enhancing the melting rates. And so it's not just it's a local source and a global challenge. So some of the connections between the landscapes, the weather and climate, and the people that are emerging from all of this really originate in our larger scale conditions. And I think Dr. Stevenson will talk more about this, so I'll just briefly go over the key pieces to keep in mind are the atmospheric waves, so the ridge and trough patterns that really drive our day-to-day weather, but then when integrated over time, drive our persistent climatic conditions and our hydroclimate. That originates largely in sea surface temperatures, or SSTs, sea ice conditions, land ice conditions, and other types of land surface conditions. And ultimately those feed upscale to drive our atmospheric wave patterns. And we know that sea ice has a very strong impact on the general circulation of the atmosphere. And 2020 is a kind of maybe a scary example, because we had record low sea ice, and some recent research has shown that declining sea ice promotes stronger ridging offshore of California, so persistent drought conditions, which unfortunately, if we look out the window, we see right now. Hopefully this is not a harbinger of what things will look like, but I'm inclined to say that it probably is. And so these local weather conditions integrated over time to give us climatic conditions really are tied back upscale to these larger scale features, such as states of the ocean and the Arctic and Antarctic. A great challenge that we have is this issue of inherited multipliers, what I would like to call our historical land use policies, our development policies. Here we are looking from a house that burned in Fountain Grove, Santa Rosa in 2017, out over the glass fire, which just burned a couple months ago. Large developments within the wild and urban interface, and historically overstocked forests that are now drying at an accelerating rate really create a big challenge for dealing with adapting rapidly to these weather and climate changes that we're experiencing. It's not doing us any favors to have to try and adapt to a new climate when you have forests that are beautiful but look the way they do on the right-hand side. And that results in some immediate challenging consequences, such as wildfires. A perennial consideration to consider within this is the idea of compounding and cascading extremes. And the Montecito debris flow is a perfect example of multiple processes occurring over many different timescales, ultimately leading to the outcome of a debris flow in the city of Montecito near Santa Barbara, with the long-term drought, some fine fuel growth during an extremely wet year, another very, very dry season, followed with a large fire, and then a high-intensity, short-duration precipitation event that kicked off a large debris flow in January of 2018. A few thoughts from emerging collaborations really include the idea that we need to bring in all jurisdictional levels to the table to have these discussions, and having these persistent interactions and discussions to co-produce knowledge across all the different levels. But we really also need to figure out ways to bring in the public as well. So a couple key points that I've found over the years that sort of seem to help this is using interesting events to motivate case studies that identify vulnerabilities and ways to address them. How to broaden engagement from diverse populations, I think, is going to be really important to get everyone to the table to help protect their environment and their health and safety. And always remember that it takes time to do this. It's not going to be one or two events. It may take years. And as a scientist, I think it's extremely important to remember to listen the whole time. It's easy to talk at people, but it's great to sit back, listen, and really hear what the issues and challenges are. So just a few last concluding remarks. To summarize, a really wonderful review paper put together this year by Dr. Amir Agu, I'm going to totally mispronounce his name, Agakuchak, at the University of California, Irvine. Climate hazards are expected to increase. We need to improve our understanding of these hazards. This is very true. However, to quote Noah Diffenbaugh, we're not well adapted to the climate we have. And even though California is a wonderful leader in climate science, climate adaptation, and mitigation, we're getting caught. Even though we can be the best at something, I think we're still getting caught by the rate at which things are changing. And so we really need to rapidly adapt our landscapes and in creative ways. And we need to really get creative to catch up to the rate at which the Earth is changing around us. So with that, thank you very much.
Thank you so much, Ben. That was terrific. A great amount of stuff. I was thinking of a transition question might be in order, but I don't know that we even have time for that. I would like to perhaps even hold that and just check back to see if Mike is online, and then maybe if not, we'll go straight into Dr. Ralph's talk. But thanks again, Ben. That was great and set up a lot of good fodder for later.
Right. Can you hear me, Mike?
All right. Hey, you're on. We can hear you and see you. So we will turn it over to you. I think your slides should be in queue. So please take it away.
All right. So here we go. All right. So hopefully you can see my slides, see the title slide there. And we'll start. Ben did a great job covering a lot of detail, so I can bounce at a nice high level here. We're going to approach this talk from kind of looking at a warming world and implications. But I want to start with this plot. And I noticed Ben shared one as well. They're a way of depicting warming, but it is relative to a period. In this case, a statewide mean temperature departure from the 1981 to 2010 climate normal that NOAA publishes. I mention this because this is 2020, and so we will soon have the 1991 to 2020 normals, and that will include 2011 to 2020. Now, if you look on this graphic and look at 1981 to 1990, and see the large number of blue bars on this that will be being removed from the normal, and look at 2011 to 2020 and the large number of red bars that will be added to the normal. That will have a great impact on how these type of plots look. Some of my colleagues, particularly those in Arizona, find that could be a bit of a challenge. And this may be the first time we really have to start to take a look at how we depict information relative to climate as we move into a more dynamic state. So a quick overview, we'll talk about the narrative of climate change for California, look at a warming world and observations, and then give my thoughts on this concept of tracking change from extremes to the commonplace. We have a nice satellite shot here of mid-October 2020, where we have a front with a nice atmospheric river hitting British Columbia, a decaying tropical system coming up out of the East Pacific, and smoke coming from California. Those two weather systems were going to merge and bring California the first precip of the year. The smoke interfered, and a wave that would have developed did not. And so we ended up with a dry October. So a really nice example of how a lot of things can mix together to create some of the impacts that we see. So our narrative, we start, I put a graphic developed by Dr. Jamie Anderson for the 2005 climate change report that the Department of Water Resources put together. And that just for the water world, there's a really nice summary graphic. Warmer temperatures, greater variability, more extremes, more rain, less snow, a longer dry season, rising sea levels, and ecosystem changes. And I like ecosystem because ecosystems can mean many different things in many ways in which things interact. And we have to figure out how, starting with warmer temperatures, everything that follows, and how we keep track of that. So let's look at temperature, and here we take data from the California Climate Tracker. On our x-axis is our mean annual temperature for the state. On our y-axis is our annual precipitation accumulation. That black triangle is our period of record average. All the blue dots are 1896 to 2000. All the orange squares are the 21st century, and you'll notice the 21st century is sampling at the warmest edge of the distribution, and the coldest years of the 21st century so far are only around the period of record average. The coldest part of the historical distribution is being left behind. All right, so now we'll focus in on the Sierra region as part of the California Climate Tracker, and we look at snowpack accumulation. So this is the April 1 snowpack statewide value provided by the Department of Water Resources. And then we have the winter average minimum temperature for the Sierra region. And so temperatures on the x-axis, percent of average snowpack on April 1 is on the y-axis. Now, April 1 is interesting because there are a lot of legal and operational elements tied to that value. It historically happens to be the average date at which snowpack peaked here in California. But looking at that, we see, again, the blue dots are 1950 to 2000. The squares are the 21st century, and the big purple square is 2020. And so what we see is we found a new part of the distribution down there in the lower right, and are starting to populate it with, have 5 squares there down right at the edge of the distribution and below. The other thing to note is that in 2014, we hit 25% of average, which tied the 1977, at that time, record low snowpack. But if you look at the 25% line and you go across, you find 1977 there just after 26 degrees Fahrenheit. You have to go over to 29 degrees Fahrenheit to find 2014. So while they had the same snowpack, they were very different environments because 2014 was much warmer. And that was followed by 2015 way down there on the right, almost near that threshold of 32 degrees Fahrenheit, and a 5% of average for 2015. Our big snowpacks of the 21st century, as you can see, are not getting up to those of the 20th century. All right, so rain or snow. Boy, this is a complex question when we talk about atmospheric rivers, their interaction with cold fronts and the dynamics that happen over a lot of timescales that Ben highlighted nicely. But if we look at it from a seasonal perspective, and we come up with a metric, worked with a collaborative group to kind of develop this fraction of total precip falling as rain by water year across the snow-bearing watersheds in the Sierra Nevada. We see, again, using that kind of departure from average perspective, that we are starting to see more red bars popping up there on the right. Really understanding seasonal as a collective versus each watershed's structure. And then, as Ben had pointed out as part of this group, even then the amount of precipitation falling during the time where you have a freezing elevation associated with atmospheric rivers really affects the distribution of moisture on the mountainside. All right, so about those atmospheric rivers, which Marty Ralph will talk more about, but I want to show the plot that Marty Ralph and his team down at Center for Western Weather and Water Extremes, big shout out to Chad Hecht for the work he does in pulling these together. But I want to show 2015 because this was the year without a snowpack. It was in the middle of that drought that Ben mentioned is on par with our medieval droughts, but also happened to contain that exceptional atmospheric river in February, where we actually were able to get high water on some streams and creeks without having the major rivers, trying to catch as much water in depleted reservoirs as we could. So we no longer have flood or drought as a state for a winter. We now have a dynamic state where you can have flood and drought coexist, because at this time you had both the flood center and the drought center in terms of operational response happening in a side-by-side manner. Really quite fascinating times. And I like to point out that these are observations now. This isn't projections of what will be. This is already what has been in this past decade. Warming worlds. Warming temperatures can be a good catalyst for some reactions, including combustion reactions. And here we're finding in 2020 just how that plays out with the top of the state's largest wildfires now being occupied by a great number of 2020 fires. We had the largest complex in the August complex, that first fire burning over 1 million acres. We also had the largest single fire there at number 5, the Creek Fire down east of Fresno. Just really some changes in when we cross thresholds that allow things to happen that haven't happened in the past. We find ourselves maybe in an environment trying to react to things we're unfamiliar with. And then, as Ben had mentioned with the Montecito event, and here's a graphic that our floodplain management team is trying to work with, is really understanding that cascading set of events and flood after fire, and trying to understand, once you have the consequences of one extreme or one impactful event, others that may follow along, and really understanding that chain of events or cascade of events is really going to be key in the adaptation process. All right, with sea level rise, have both temperature and volume effects in the oceans, but you also have the land surface subsidence and uplift considerations, and understanding how all these play together. And so we kind of look at the 3 plots that we use in our hydroclimate report for the Department of Water Resources. We have La Jolla, Golden Gate, and then up there at Crescent City. And then understanding that north of Mendocino and the Mendocino Fracture Zone, you have the subduction zone where the Pacific Plate is diving under the North American Plate and providing some uplift. What happens then when it collapses back down is you get step changes in rather catastrophic events. And so trying to figure out how all these forces play together, work within the variation in tides over the tidal cycle in 19.6 years, and events like El Nino, La Nina, and events like storm surge. And February 2019 is a really interesting case study in that. All right, so next now I want to talk about distant change and its impacts on California, because we don't have to just consider what's happening within our state boundaries. March 24th, 2018, Typhoon Jelawat forms in the Western Tropical Pacific, and you might say, well, what does that have to do with California? Well, its remains actually came across the Pacific and became the first decaying typhoon to hit California in April. The 5 previous decaying typhoons happened in October. So when we have enough heat in the tropical oceans to spawn typhoons in Northern Hemisphere spring, their remnants can come across with the jet and impact California. The other one I want to show you is, again, this year's sea ice as we work our way into fall, and we start to see the Siberian plain being covered by snow. And understanding these large-scale dynamic conditions impact the way that general circulation works, and Ben showed a nice image of that, but really understanding where your thermal pole can be. Was it that permanent ice field in the Arctic Ocean, or does it temporarily shift over into that Siberian plain, depending on what your ice cover and snow cover are? Really understanding more of these dynamic states are going to be important. Some nice list of extremes there. If you want, you can pull up my slides later to look at. 2020 was quite a year in terms of variability extremes, including decaying tropical systems from the East Pacific, making landfall north of the Golden Gate, and the lightning storm that spawned the over 700 fires in Northern California. Most active Atlantic hurricane season in the U.S., setting new records in those billion-dollar disasters. All right, so from the extreme to common, this is what I wanted to finish with and really kind of talk about, because here we have the minimum temperature for California in a water year perspective. And so really having to understand how I'm packaging the data. A water year starts October 1 of the year before and ends September 30 in the year that we mark it. So we are in water year 2021 right now. But what we have here is the minimum temperature for the year. And I drew a line connecting what was an extreme in the 30s. As you see, from the 30s to 1980, and in the 80s and 90s, it started to become episodically crossed. And then as we get over past 2010, it becomes common. That threshold has been crossed. And so there are a couple points here. What we once thought was an extreme, we're now starting to see episodically and may become common as things continue to warm. The other element is there are thresholds. As we cross those thresholds from what was an extreme to episodic to common, there are those cascading impacts. Temperature, you can have reactions, you can have things like harmful algal blooms that suddenly go from being a rare event to being a more commonplace event. And so as we have our indicators, really understanding not only what we're tracking, but understanding we're tracking when it's an extreme event, when it's an episodic event, and when it's become commonplace. And the last point with this is that this is not the new normal. This is the jumping off point. We're leaving that historical distribution behind, carving out new territory, but we're not stopping here. The world is continuing to warm, and we're moving then into a dynamic state where not only do we have to worry about looking at what's at the mid-century or end century, but how is that next decade going to look, and how can we figure out how to adapt and what to expect in that coming decade? And with that, I'm done. So hopefully it didn't go too long, and we'll stop there.
Great. Thanks so much, Mike. That was wonderful, and some more great information that really feeds off of what Ben was talking about. I'm going to just keep us moving just for the sake of time. There's so much to come back to. I appreciate it. Again, thanks, Dr. Anderson. So I am going to turn to Dr. Ralph. And he is the next in the lineup here, and we'll be focusing on atmospheric rivers. And so we'll get a deeper dive into some of these offshore processes and how that affects California and other places. So with that, Dr. Ralph.
Thank you very much. Can you see the screen and hear me?
Yes, perfect.
Great. Well, I'm going to shift gears and build on what we just heard from Dr. Anderson and Hatchett, which was a very multi-phenomenological summary to focus on one storm type, atmospheric rivers, and I'll tell you a bit about it from a variety of perspectives. But I want to diverge for just a moment. Following the inspiring lead of Tribal Chairman Lopez and Secretary Blumenthal and science icon Ben Santer, and reflect for a moment personally on something I experienced recently that I think relates to what we're talking about here. I had the chance last summer to visit Sequoia National Monument on the Kern River, and walked off trail for a while and found this little pocket meadow full of giant sequoias. It was one of the most inspiring natural experiences I've had. The size is hard to fathom from these pictures, but they were unbelievably large, giant. There's an example of a ragged old one standing up. And then this SQF fire complex hit sadly in September. And to see what happened, I was up there just last weekend, and here's what this looked like. This is looking down on the ground. You can see the devastation of the fire. Some of that could be viewed as helpful, right? Replace nutrients in the soil and the like. And the sequoias are, evolved for fire. But it was devastating to see this. And sadly, some of these giant trees even burned all the way to the top. This is clearly something on the order of a 200-foot giant sequoia here, totally devastated. Other trees, like the one on the right there, had char halfway up. And if you look carefully, it might be slightly out of scene. That tree on the right had burned at the top, and part had fallen off and crashed to the ground over here. That tree, clearly something on the order of 1,000 years old, gone or changed. And at the same time, there was, in other pockets in this old growth forest, still this inspiring beauty. When Tribal Chairman Lopez referred to the indigenous people's view of the land, I had that moment in that place last summer and felt that connection that is so important to many of us. And to see this devastation just touched me deeply. The scene on the right gives me hope. The scene on the left gives me doubt. I really appreciate the chance to be here today and share some of the work we're doing on atmospheric rivers, all with an eye towards hoping that we can manage the situation over time. All right, well, let me turn back to the technical. This is a diagram that highlights, basically one of the main challenges we face in California is our climate is more variable in terms of precipitation than anywhere else in the country. Here in the east, where I was from, total precipitation really varies only slightly from year to year. Plus or minus 10% would be a wet and dry year. Here in the west or southwest, it's plus or minus 50% in some places. And we can have one year be 40 inches as the average up in the Sierras, down to 20 inches the next year, or up to 60 the following year. And those are sort of the standard deviation of the climate we have here. And it turns out atmospheric rivers are one of the main drivers of that. We live in a Mediterranean climate down here in the south, especially a little bit up north as well. And it turns out that these singular storms have a big impact on our water supply. In fact, on the right, we see from a paper by Gershenov et al. In 2017, the annual percentage of precipitation from ARs across the entire West Coast is on the order of 20 to 70%. I think in California, there are places that are 40, 50, even 60%. And you can see even penetrating inland to the Intermountain West and into Arizona, we see 30% in some places. So these are important players. You saw a map from Mike Anderson that showed sometimes very few ARs hit, sometimes many hit. That really determines our outcome in terms of water supply. They're also, of course, when they stall and they hit on an already wet area and they're strong, they can cause flooding. Here's an example of one from the Russian River a few years ago, and our early study on atmospheric rivers that first documented that ARs can cause flooding was done on the Russian River. And we looked back and found over the previous 7 floods, all of them had been associated with ARs. And that began what now is the knowledge of ARs are the flood makers in the West. And in particular, a very nice study by Corringham et al. In Science Advances published last year showed that these dots on the right are looking back at 40 years of FEMA flood claim damage data that, like in the Northwest coast, there 99% of all flood damages over 40 years were associated with AR storms. And you can see basically it's in the 90+ percentile in Northern California. It's in about the 80 percentile in Southern California. So it is the dominant storm type for creating flooding. To help distinguish a bit between the potentially beneficial storms that provide water supply from those that provide flooding, of course, sometimes the flooding ones can be beneficial for filling reservoirs. But we've developed a scale that ranks ARs from 1 to 5 to characterize their strength and their impacts. And I just want to really highlight one unique aspect of this scale relative to, say, the hurricane scale or tornadoes, both of which hinge on really one variable, essentially wind. And here we have 2 variables. On the vertical axis is the strength of the water vapor transport horizontally in the AR. Think of it as if it was a terrestrial river, how much water is flowing down that river, how fast it's flowing. On the horizontal axis, though, is the time that AR is over a given location. So if it lasts 24 to 48 hours over that spot, you can go up the axis there from 1, 2, 3, 4 to 5. But say you're at 600 max integrated vapor transport, and yet it lasts over 48 hours at least minimal AR conditions, we upgrade that from a 2 to a 3. So we have an adjustment there. And it's been a part of a problem for the hurricane scale that they haven't been able to, that does not factor in when storms stall, like Hurricane Harvey and Florence, both of which were relatively weak on the category scale for hurricanes, but because of their stalling, they produced all this heavy rain and the damages were terrible. Here we see an example of a composite of how an AR, all the ARs 5s that hit Bodega Bay, the star there, this is the average precipitation distribution over the 2 days following that, anywhere from several inches to nearly 10 inches. And then we took the scale and compared it to the damages, and we see this logarithmic increase in the damages associated with ARs of different rankings, where the mostly beneficial ones, ARs 1 and 2 don't do much damage. The median damages are less than $1 million each, but they provide really beneficial water. However, when we get up into the AR 4s and 5s, we see damages median in the 10s to hundreds of millions. And you can see the 3s, 4s, and 5s, those top dots, those can be billion-dollar events. An AR3 coming on the heel of an AR5 can create major damage, or an AR5 hitting a very dry and unpopulated area has less damage. So there is variation there, but these medians are based on many years of data. So I'd like to turn for a moment to a very important topic we've been working on called forecast-informed reservoir operations, because our reservoirs were really designed some decades ago, for the most part, to handle, wet winters where some flood control capacity is needed and dry summers where it's all about water supply. And I want to show you the example here from Lake Mendocino in the northern Russian River. The vertical axis is the storage in the reservoir. Horizontal axis is the water year, October 1st to September 30th. The gray dashed line is what's called the rule curve, and that's the rule that was built or designed when the dam was built some decades ago, and says basically in the winter, keep it a little bit empty in case there's a flood. And notice the blue line here. Well, there were two big ARs right there, and they encroached into the flood pool. And then per normal operations, they released the water to restore that flood pool in case there'd be a storm coming in the next 2 days. And what happened though is the winter let up, and the blue line here, you see it descended into drought. And this became a very serious drought with water shortages and rules and issues for salmon and the like. Now notice the green curve is the following year, and notice how different it is. It was a preceding year actually. Notice how the green line here ramped up and stayed high. That's because that heavy rain came in March, a miracle March event here where the reservoir refilled substantially, but because it was late enough in the season, they were allowed to keep that water. The same amount of precipitation, that's these dashed lines down here, happened in both years, but the timing of that precipitation differed and the rules differed because, related to that. And here now we are working on looking to see if it's possible to keep some of that storm water safely, hinging on there being a forecast of no AR coming, because it's only AR storms that produce flooding on this watershed. So if there's no AR in the forecast for a few days, keep that water or some of it temporarily. And if a storm is predicted, an AR is predicted, there'd be a few days to release that water. So we see now we're doing this similar sort of approach with the Army Corps of Engineers and local water agencies shown in the right, sampling different geographic areas from coastal, rural and the Russian River to high Sierras and, part of the big water supply for the state, Lake Oroville, and then down south in the very urban area of Southern California, Prado Dam on the Santa Ana River. Well, one of the things we're doing to improve the forecast is, so improving the forecast can help achieve greater flexibility in operating reservoirs, potentially, and that's what we're testing with the forecast-informed reservoir operations, and I'll show you in a moment the early results. Here we have an example of trying to improve the forecast of ARs by flying Hurricane Hunter aircraft out in the storms in the winter. We've been doing this for 5 winters now. We're going to do it again this year. It's become operational. The diagram shows the orange and yellow color fill is the AR offshore. The black lines show where we flew the 3 aircraft, and the dots show where we dropped sensors drop into the atmospheric river, and with radio signals back to the aircraft. We then took that data and sent it to the global weather prediction models, where they then incorporated into their forecasts and made the forecast better. And here you can see for perspective, the red dots on the left are our domain for the dropsondes and how that compares to upper air data, as we call it, available from other ground-based sites. Essentially, we created the equivalent of about half of Western North America in terms of aerial coverage over the Pacific, and that had more impact on the forecast skill than the entire North American continent in terms of upper air data. And our center at Western Weather and Water Extremes at Scripps Oceanography, UCSD, is a co-lead of this project with the National Weather Service. Another thing I'll just highlight is a tool we have. I don't want to explain it in detail for time's sake, other than to say that we're looking at AR landfall along the coast, the dots here, the black dots on the right, and we're looking out 16 days into the future. That's the blue diagram going left. And where we see this colorful blob, that tells us that about 5 days out, up here in Northern California, we should have high confidence there'll be an atmospheric river hit. In fact, this one was going to be focused most in Central California. We've been developing these tools and they're feeding into the forecast-informed reservoir operations effort. In addition, we're developing a special weather model for the West. I won't go into details here, but we call it WEST-WRF for Weather Research and Forecast Model. And it is running in real time in the winter. And on the right, you see the national models or colored lines are showing their boundaries. They don't go very far offshore. And here we have the outer domain is our WEST-WRF domain. So we get very much farther out and we do higher resolution, the red box over the state. Now, the result from this FIRO study on Lake Mendocino, we started it as a paper study, but it turned into a real reservoir operations demonstration. And with the Corps of Engineers approval and the Sonoma Water Agency's approval, the reservoir was operated differently last winter. And here we see that water year summary from, in this case, it goes out into April. But the black line is what was actually stored in the reservoir. The brown line is what would have been stored without FIRO, and it includes 19% increase in the amount of water available for this summer. And this happened in the third driest year on record for this watershed. The gray shaded area here, the light gray, is what we call the FIRO variable buffer pool. That gives the reservoir operator flexibility to operate the dam to this new method. Now, I want to highlight that this is very experimental, and that we're working closely with the Army Corps of Engineers and with other water agencies to study the potential of this in the Sierras for the Yuba Feather system, and in Southern California for the Santa Ana River and the Prado system. It's very promising, but every reservoir is different, and the needs and information decision-making is different, and the storms themselves might differ a bit. Finally, I'll just close by highlighting a little bit of a longer lead, S2S we call it, subseasonal to seasonal prediction out to 2 or 3 weeks. And then turn to the final point I'll make is about the fact that atmospheric rivers are now recognized in the National Climate Assessment as as a new storm type under the Extreme Storms chapter, where now atmospheric rivers are going to be examined in much more detail from a climate standpoint. We have evidence now on the left here from a paper, Gershonov et al. Last year, that shows that percent change in the contribution of ARs to total precipitation. Those blue colors mean basically ARs are going to become even more important to water supply. And on the right-hand side here, we see diagrams that show on the vertical axis the precipitation frequency change, looking at climate models for the Russian River Basin at the top and the Santa Ana River in the south. Just focusing on the north for a moment. The punchline is we see these on the horizontal axis is the daily precipitation percentile. So what we see is a reduction in the relatively light rain days and an increase in the heavy rain days. And those dark gray bars are almost the entire bar there, which says those increases in very wet days, the role they play in annual precipitation, that ARs are really the culprit there. I'll just highlight in closing that the work we're doing on atmospheric rivers and on forecast-informed reservoir operations has gained the attention of the Oversight Committee for National Water Policy. Congresswoman Napolitano here chaired that committee, and we had a briefing a while back about this last year, I think it was. And they're very interested in seeing us continuing this work and appreciate the feedback they get from water agencies about the importance of it. Finally, I'll just mention there's a book just came out on atmospheric rivers if you're interested in more. It's the first of its type and many contributing authors. And I'll close with that. Thank you very much.
Great. Thank you, Dr. Ralph. That was excellent and a lot of material. Once again, we have another great session. I mean, just the economic implications, the forecasting, the outlooks, that there's a lot of things to digest here, but I'm going to keep moving on to our next speaker. This is all going to come back in our discussion session, hopefully. The next speaker in the lineup here is Dr. Samantha Stevenson from UC Santa Barbara, and she'll be talking a little bit more about some of these large-scale processes and what those implications may have for some of the extremes, whether acute or longer-term emerging extreme events that has to California and elsewhere. So Dr. Stevenson, thank you.
Okay, great. Can you hear me and see my slides?
Yes, perfect.
Perfect, great. It's always a challenge. Okay. So yeah, I think that what I'm going to say is really really builds on what the previous speakers presented. And so I'm going to be focusing primarily on the types of large-scale climate dynamics that operate and have relevance to California. And I think other speakers have really done a great job covering the extremes themselves and their overall behavior and trends. So I'm going to talk a little bit about the mechanisms here. Okay, so just so we're all on the same page with what I mean when I say mode of variability. So in the climate system, there are these patterns that emerge, which are typically very large. So they operate on the scale of entire ocean basins. So actually, like the title slide that I showed was a picture of an El Nino event, and there's warming that happens over the the majority of the equatorial Pacific, for example. And that's just one example of a mode. In general, these things involve large-scale coupling between the atmosphere and the ocean. And so we're seeing like things like convective reorganization in the tropical Pacific that then communicates with through the atmosphere to places like elsewhere around the world. And these can operate on different timescales. So I'm going to focus primarily on the timescales of multiple years to several decades, but there's some indications that there are both shorter and longer term modes as well. I just can't do justice to every mode of climate variability around the world in 15 minutes. But yeah, so trying to understand these modes is really important, because although there's a lot of internal variability in the climate system, so no matter what you do to the ocean, there's always going to be like the atmosphere wants to do what it wants to do to some extent, so there's going to be some kind of like weather randomness involved. But these types of modes and these changes in particular in oceanic conditions have the potential to affect the statistics of weather and climate extremes, really in a lot of places around the world, but in particular in California. Okay, so that's what I mean by a mode. So I guess I studied the El Nino Southern Oscillation, and so just to get us a primer on how this works, this is largely the alternation between an El Nino event and a La Nina event. So here's a satellite image of sea surface temperature anomaly during a major El Nino event, which happened in the winter of 1997 to 1998. So El Ninos are characterized by a weakening of the equatorial Pacific trade winds, which is generally blowing from east to west. So the anomaly is from west to east. And that allows as I mentioned, the majority of the equatorial Pacific to warm. Although I don't have time to get into this, but every El Nino, the pattern of that warming can be slightly different, which then matters in terms of its atmospheric impacts. Right, but in general, we're seeing that an El Nino event is associated with these weaker trade winds, this warmer SSTs, and a deepening of the equatorial thermocline. So that being the kind of pool of warm water that sits in the surface ocean. The counterpart to El Nino is a La Nina event. So here's just another example in 1998 to 99. So often strong La Nina events will follow strong El Ninos. And we have another example that happened more recently in 2015, 16, and 2016, 17. But these are the better satellite images that I had. So a La Nina event is characterized by a strengthening of the equatorial Pacific trades, which brings with it a colder SST anomaly in the eastern to central equatorial Pacific and a shallower thermocline. So this is associated with like stronger equatorial upwelling and the production of more primary productivity in the oceans, so supplying more nutrients to the surface waters. So this is really important for fisheries as well. So I'll be trying to switch back and forth between like atmospheric and oceanic impacts throughout the course of the talk, because for management purposes, both of those things matter. Okay, so I think one of the previous speakers mentioned the idea of El Nino teleconnections. So I'm not going to get into all of the mechanisms here, but essentially these warming patterns that we see, or cooling patterns, during changes to the phase of ENSO, or the El Nino Southern Oscillation, bring with it these propagating atmospheric wave patterns. And the structure of that is, the structure which is important to different regions can vary. In California, we're typically seeing that during an El Nino event, you have a strengthening of the low pressure pattern that sits off the coast of California, and that leads to a wet anomaly during an El Nino. Okay, so typically in Southern California in particular, we're going to get wetter conditions in the winter. Right. Although this is not the case for every El Nino event, as I mentioned, there's going to be a large degree of internal variability that leads to El Ninos having different impacts. But in general, we're kind of loading the dice towards a wetter winter during an El Nino. So this has implications because the state is, of course, very vulnerable to both drought and flooding. And I just pulled a picture from the US Drought Monitor from, I guess, the day before Thanksgiving. And so we are now we're not in severe drought conditions during most of the state, but in Southern California, we are in abnormally dry conditions. So as Dr. Ralph mentioned, we can sometimes look for these atmospheric river events to replenish some of the snowpack and soil moisture anomalies to break the drought. And so there's one school of thought that says during an El Nino event that's going to favor the propagation of atmospheric rivers into Southern California and tend to enhance the buildup of soil moisture anomalies, and in Northern California to favor the development of larger snowpack. Just for some other context of what's going on right now, we're actually in a La Nina at the moment. So this is perhaps contributing to why we're seeing dry anomalies over much of the California at the moment. So this is just a picture of the SST anomaly at present, or I guess as of November 4th. So it's colder than average over the majority of the equatorial Pacific. And so this is what's considered like a fully developed La Nina event. It's projected to continue through the majority of the winter of 2020 to 2021. And so one might think that La Nina event is going to be associated with further drying conditions. So, all indications are that we're going to continue to see relatively dry conditions in a lot of California. So I mentioned that because of these teleconnected impacts, El Niños and La Nina events can have drastic influences in terms of the extremes. So just, a couple of examples. I think this is the 82-83 El Nino, if I remember correctly. But there's been some historic extreme flood events that have occurred during El Nino events. And this has kind of led to this body of research that focuses on the statistics of the associations between El Nino and precipitation in California. So in this particular case, there were these really extreme rainstorms that happened during the El Nino winter, which contributed to erosion in the vulnerable hill slope areas. You can see, whoever owned this house was not having such a good day that day. It can also have impacts on the magnitude of waves. So when you have an El Nino event, then that can affect the direction of propagation of oceanic waves, and so you can that can contribute to increased coastal erosion in cliffside areas as well. So yeah, there's drastic impacts on flooding and erosion. And I think this slide actually was shown in the previous talk, but it's just a really nice illustration of the integrated water vapor content of an atmospheric river. So I just wanted us to have a visual to go along with this idea that the variability, large-scale climate variability can affect the variation in atmospheric river propagation as well. And I deliberately didn't try to summarize that entire body of research because it's still ongoing. And my understanding is that there's the magnitude of just random variability in the atmosphere can be quite large, but there are some indications that during El Nino events, the trajectory of atmospheric river making landfall in California can be altered. So I think they tend to be somewhat more further south during El Nino and further north during La Nina. But again, there's like a lot of variability in that. So then just moving on to some oceanic impacts so here's a couple of examples of recent strong El Nino events and the associated SST anomalies in the California current area. So you'll see that in general, the El Niños are associated with strong warming off the coast of California. And so this is quite important for managing things like local fisheries in the California current. But the structure of SST anomalies does seem to differ across these different El Nino events. So the 2015-16 event in particular was characterized by this extremely large scale warming. And it was, in fact, there's a body of work on this idea of the blob. So there was this gigantic blob of warm water that sat off currently covered the entire coast of California, as opposed to being very localized near the coast, as we saw during 82, 83, and 97, 98. And so this is considered like what they call a marine heat wave, and was related actually to atmospheric forcing. So there's this feature that was nicknamed the ridiculously resilient ridge. that it's basically a high pressure system that sat off the coast of California for multiple years. And the circulation around that high pressure system favored the development of that large blob of warm water in the North Pacific. So this wasn't a direct result of the El Nino, but they did interact with one another, right? So we had the ridge set up, forming the blob, which then allowed the El Nino events in 2014-15, which was somewhat smaller than 2015-16, to persist, right? So it looks like there's the interaction between mid-latitude variability and tropical variability can be really important in determining how persistent these types of extreme events are. Right. Then I just wanted to briefly point out that the ENSO isn't the only game in town, right? So if you consider the variability in climate on longer timescales, then there's different modes that come into play. And in particular, there's this idea of the Pacific decadal oscillation. So there's actually variability in the North Pacific that tends to be, it has one center kind of further out into the Pacific. So in the central North Pacific Ocean, that's where that blue anomaly is, so that cold temperature. And this is considered the warm phase of the PDO because there's warming along the California coast and like the Eastern Pacific. And if you would zoom out on this image, you would see that it's got a very El Nino-like warm anomaly in the equatorial Pacific as well. So the PDO is in some sense considered to be what you get is like the low frequency, not component of ENSO, but it's a response of the ocean to that long-term low frequency atmospheric noise, which then modulates what the tropical Pacific is doing. So it's a little bit unclear how independent the PDO and ENSO are from one another, and that's another topic that the climate community is really interested in understanding, because you probably need to understand the statistics of what's going on in terms of mid-latitude atmospheric variability to predict what's going on in the tropics and vice versa. So just to show you some of the statistics of rainfall anomalies that are associated with both the PDO and ENSO. In general, like as the SST anomalies, the rainfall anomalies look somewhat similar. So in general, when you have a warm phase of the PDO, you're going to have more rainfall in the southern tier of the US, including the southern part of California. And so this kind of says that it depends on the time scale that you're thinking of, right? So if you're considering an El Nino winter, then that would be more likely to see a wetter winter in the southern part of California. But if you think about this on longer time scales, so maybe like the PDO varies on time scales of decades, so multiple decades. So then you might say, okay, well, we have an El Nino winter within this, say, 20-year period where the PDO has a positive phase, so we're already in kind of a wet period, right? So it depends on the types of statistics that you're interested in. And then I wanted to just, as I said, I don't have time to talk about every single mode of climate variability, but there's another really important climate mode operating in the North Pacific called the North Pacific Gyre Oscillation, which looks somewhat similar to the PDO, but is independent. So it has, it's characterized by sea level pressure anomalies that are centered slightly further south. And there's actually, two different lobes of variability. So that's what's shown on the left-hand plot there. So we've got one center near 50 north and another near 30. And if you look at the oceanic impacts of this, then it turns out that the NPGO is really important for driving coastal upwelling in the southern part of the California current system, so the part that's circled in blue on the left. If you make indices for both of these modes, then they're very, very strongly correlated. So trying to understand how these modes work is really important for, say, understanding like when there's going to be the next marine heat wave or that sort of thing. And then I just wanted to briefly close with some considerations with, related to climate change. So it looks, although we do understand to a large extent how climate trends are going to behave in a lot of these climate models, climate variability is one of the major frontiers of uncertainty that's still left, right? So I think the idea of a large ensemble was mentioned maybe this morning. But here is just an example of the strength of ENSO variability in 2 of those large ensembles. So basically, you've taken 2 different state-of-the-art climate models. One is called the CESM, and the other is called the ESM2M. Those are just acronyms. They're both quite good. And what the modeling centers did was run each of them multiple times. So I believe it's 30 or 40 times in each case, varying the initial conditions very slightly. And so then what I'm showing here is a time series of the running variance. So the variance in 30-year chunks of a moving window that slides from 1960 out to the end of the 21st century. And that's of sea surface temperature anomaly in the Niño 3.4 region, so in the central equatorial Pacific. And so the point I wanted to make here is that in 2 very good climate models, you can have one that's predicting an increase in the amount of variability in the ENSO system, and one that's predicting a decrease. And it's unclear exactly who's right at the moment. So in that sense, it can be difficult to project the net influence of ENSO overall. However, what the models do seem to agree on is that for a given El Nino event of a given magnitude, the impacts of that El Nino are going to be more severe. So here's those, some results from those same 2 models that I just showed. And this is the effect of the regression of rainfall onto the Niño 3.4 SST anomaly, but essentially the amount of rain that you can expect per degree of El Nino related warming. And as I mentioned, like it's an increase in precipitation because through the majority of the southern tier of the US, including Southern California. In the left-hand panels are showing that what happens in the historical climate, so in present day. And then the right-hand panels are showing the change. And there is some difference in the spatial structure of those patterns. But if you focus on California, you can see that both of those models agree that if you have an El Nino, it's going to bring more moisture into California, although they might not agree on exactly how big that El Nino is going to be in the future. Okay, so yeah, that's all I had. Just to summarize, there are many different climate modes that influence California. And I should also mention that there's not only tropical modes, but there's also higher latitude modes, which include some of the polar regions in some cases. And their importance is variable on different time and spatial scales. So if you're considering years to decades to multiple decades, then the mode that you care about might be different. And the random variability also cannot be neglected. El Nino events are different from one another, and they're also influenced by what's going on with these other mid-latitude climate modes and with atmospheric noise. That said, these climate modes can, in some sense, load the dice for extreme events. So they'd say, well, we don't know that specifically what's going to happen in this particular year unless you do something like a seasonal forecast. But we're going to see that statistically these things are going to change. And it's unclear how the modes themselves will change in the future, but we do think that their impacts are likely to intensify. Okay.
Awesome. Thank you, Dr. Stevenson. That was great. We are running just a touch behind, and so I'm going to see. Normally, I think we had set up for just a 5-minute break to just catch our breath from all of that, and then come back and convene for very specific questions and sort of the panel discussion. I want to just make sure we still want to do that, and so I just ask maybe Orit Kalman if that is still the plan of action, or if we should try to just move right into some of the questions that we might have.
Yeah, thanks, Michael. Yeah, great presentations. We are coming close to our lunch break, which is at 12:15. So I would suggest that we just spend the next 13 minutes or 15 minutes that we have just having a conversation. It looks like there are a couple of questions in the Q&A panel, so I would just turn it to you to engage your panelist, and we'll plan on, right as we break for lunch, to pose the panel question for Dr. Hatchett right as we leave. So I'll just turn it back to you.
All right, thank you. I'm seeing a couple of those questions, and I guess I'll just ask the panelists to put back on their video. I suppose that's the best to kind of see folks, so we can have this discussion. And I'll be checking the chat a little bit here, but I do have a couple of questions along the way just to sort of bring out some of the topics that ran through all of the presentations. And certainly scale is one of those, and sort of a heightened sense of maybe shorter time scales that we should be thinking about. But I wanted to first start with Dr. Anderson. We'll put you back into first place. I know you went second, but back into first place on just, you brought up some very intriguing information about sort of maybe a new normal, or this idea that we're entering new phases or unprecedented territory. It has an element to how we may think about indicators, new indicators. And if you wanted to punctuate that any further based on your talk, and also if you had any advice on what variables we should be measuring now, or indicators that we're not currently maybe capturing in the spirit of maybe thinking for this next report or beyond for California. So I'll leave it there and start that question for you, if you don't mind.
All right, thanks, Mike. So I'll build on the idea a little bit here. Starting with, so in 2015 and 2014, we saw those record warm temperatures. So we kind of moved outside the historical distribution. And that was our first foray, the extreme. And the rest of the 21st century is kind of hung out in the warmest part of the distribution, with our coldest year kind of being period of record average. Now, we think with continued warming, we'll see new extremes. Those extremes of 14 and 15 become episodic. We start sampling a little more frequently there. And so it's not that we just stay where we are now. Climate is no longer a static baseline with which we can say this is what is and what we can expect. We now have a more dynamic state where we have where we are now, but we're moving. And climate, if you think of the climate state as being in an equilibrium, when you're out of equilibrium, you experience a shift, and you're in that period of shift, so you're moving. Understanding then in terms of indicators, maybe we need to think about not only that concept of thresholds, right? Where are those important thresholds where we start to see some processes happen, some new things that happen but start happening faster, things that have impact on public health or elements of our economy, our natural systems that we find will have significant impact on our lifestyle. If we think about anadromous fish, cold water fisheries, where above certain river temperatures, the water is lethally warm. And understanding, well, what are those things we track? How do we track them as an extreme event, an episodic event, or a commonplace event? What are our adaptations as an extreme? What are our adaptations as episodic? What are our adaptations as commonplace? What do we have to do to shift? But then also thinking, how quickly are we getting there? And that was that idea of looking to the next decade. How quickly are we going to move through this? And so you start to think, what are indicators that give us a sense of velocity? Which is a really kind of weird concept to wrap your head around when you think about things that we're taking long-term averages of. And we have this kind of operating perspective that that's a static entity. And so now we have to think of it, sorry for the math here, everybody, but in the first derivative of we have its position, we have its velocity, and then maybe that second derivative, we have its acceleration. We used to deal with position. Now we have to start thinking about those first and second derivatives and how do we measure what we see in the world? How do we derive from those measurements those elements of position, velocity, and acceleration? I don't have any specific ideas yet on how to do that, but I figure we have to start doing it.
Marty here, could I pile on that?
Absolutely.
Yeah, I think Mike's onto something there with the, trend is another way to put it. And the second derivative of the trend, or, is the acceleration. So I'd like to point to a couple ideas real quick. One is that we have these extremes from year to year now have become quite extreme, from the driest to the wettest year in just 2 years. And that is a hallmark of what we expect to happen more. That might be a metric that would be interesting to, pretty straightforward to calculate and see how the variability from year to year is changing, or over 2 or 3 or 5 year timeframes. Another one would be, I think, because atmospheric rivers are so important to the water supply and our flooding, a very simple count of, are we changing the number and intensity and duration of ARs, hitting the state? And those, because they provide much of the water, matter a lot. Another one is snow level. So what's the altitude at which snow is falling versus rain is tied to the temperature changes that Mike showed there. So anyhow, those are 3, simple examples, I think, where we could start tracking.
Hey, I got a question for Mike or Marty. Alan, what's the time frame that you think about if you talk about first and second derivatives? How long do we have to go back, and how quick is it changing? Do we have enough years in the last 20 years to make that analysis?
Oh, Alan, that's a really good question. It's hard to tell because we think of the climate normals as these 30-year windows that we say, okay, within this 30-year window, that identifies our position. If we want to think about then the movement of that position, we would need a longer record to get to understanding the ability to detect changes in that position. Then we start looking at our observed record capability, either with satellites at 40 years or our instrumental record, if we're really lucky, we get 100 years. More likely, it's about 60, 70. Really only at the edge of being able to do it. So this is where you have to start figuring out, are there clever ways to tease it out without having all the information to do kind of your fully principled, and if you had everything nicely and neatly for you. It's not as straightforward to calculate it as you might hope. But we can't wait until we have enough data to do so, because we're seeing signs that, boy, these extreme events are really starting to push the boundaries of what we're comfortable with.
Yeah, and I think to add on what Mike was saying, and the question is that what's really cool in California now is we have a lot of these investments over the past 10, 15, 20 years on really novel observation systems that, because they've been there and they've been supported and sustained, now we can start leveraging that to look at trends in more kind of novel approaches, like snow level is a really good example, or water vapor from GPS is another example, or some of these other very high resolution perspectives of the atmosphere, like from the vertically oriented profilers along the coast that tell us the winds in the vertical, not just every 12 hours, like with balloon soundings, but every 10 minutes or every hour. And I think starting to stack those up in terms of indicators and every year adding on to them, like Mike and his group do with the DWR hydroclimate reports, I think is a really neat way to start adding more and more and more evidence and insight and information into the problem as a whole. And then we're pretty lucky to have these kinds of observation systems. And I think it's really important that we keep supporting them and keep them going so that we can really start tracking them and have enough data to evaluate not just the linear trend, but the derivative of that trend as well, and see if it's accelerating, see what its variability is, start tying it to other modes of lower frequency climate modes, oscillations in the atmosphere and oceans.
Yeah, I agree. And again, just to build on that, absolutely, we should be continuing every long-term climate monitoring we can, and probably doing more. But I was excited to see in some of the previous talks the use of paleoclimate data. So I think that's another thing that we could be pushing and saying, like, well, we do have these, especially in the case of tree rings, like we have 1,000-year records of drought. and are we using those as effectively as we could be? Or maybe there's additional statistics that we could be doing to say, like, what, maybe we understand what the 100 or 500 year drought return period might be better than we think. So just something to keep in mind.
That's great. That sort of builds on this. What are the boundaries? What are the historical boundaries? Are we pushing those boundaries more and more as we advance through time? I do want to kind of stick with this scale thing. Maybe another aspect to it is are you folks in your work, in your day-to-day work, being asked for more real-time information? This sub-seasonal and seasonal came up several times in the discussions, and it seems the time is now, and to advance those systems, we're looking to provide those outlooks and those forecasts. Maybe you can comment on that. And then I just want to throw something out there on wildfire, and maybe that is directed more towards Ben, since he was talking most about that. But let me pose that to the group and then maybe follow up with some wildfire.
Yeah, the real time, the interest in and requests for real time information are overwhelming, and it's part of the reason our center is developed at Scripps, is to respond to those needs at local, regional, state, and national levels.
And I think a really interesting piece, and something I kind of alluded to at the end of the talk, is the value in having this real-time information and being able to really rapidly, kind of like attribution, but rapid contextualization of being able to tell someone very quickly, this is the most extreme thing we've seen in 10 years or ever, and being able to allow people who are responsible to respond to these events to go, oh, I need to go quick because this is really bad and we haven't seen this before, and then also to be able to share that with the general public so that they can get a better understanding of, oh, we've never seen that, or this is pretty wild, or no, this is run of the mill. And then on top of that, I think that also helps place some of these compound or cascading impacts into better context as well, to understand, okay, when you have a sequence of kind of normal-ish events, but if they all occur in the right order and at the right are phased correctly with one another, that's how you can get a really notable outcome out of otherwise a juxtaposition of not really too far out of the extreme events.
Great point on the communication and the contextualizing that information for people so they understand. Hopefully plays a role in sort of the urgency of matters and how all of these things are connected. I just want to do a real quick time check and make sure, I think there's some additional questions maybe in here.
So Michael, thank you for doing the time check. I think given that it's 12:15, we're going to have to cut the conversation short, which is my least favorite part of being a facilitator, and recognizing that we're also not in the same space together. So cutting it really means that we're not continuing the discussion. So just really want to encourage people to use Slack to pose the questions that have not been answered, and really encouraging our presenters to engage with participants that way. So want to thank you, Michael, for facilitating and moderating the discussion, and thank you to all our presenters. And I asked Mary to put up Dr. Hatchett's poll question as kind of an exit into our lunch break, and we will continue with the next two sessions at 1 p.m. So here is Ben's question. How can we engage the public and increase buy-in to motivate the rapid adaptations necessary to address the suite of challenges introduced by weather and climate extremes in a timely manner? So I think that was something that you brought up in your discussion, the importance of not just what we're doing, but how can we do it quickly and in a timely fashion. So we'd love to get everybody's thought, and we'll post it at the end of the minute, and see you after lunch.